This is the water heater control I got from China. These are only about $2.80 each, and it costs about $6 to ship them. So I was supposed to get two for $11 and something. That included tax, which isn't a bad deal. But I only got one, and I asked for a 24-volt one, and I got a 12-volt one. They're probably the same board, but the 24-volt one will blow up because it'll put 24 volts on the gate of a FET. So anyways, I'm going to modify this one, and I'm going to do it step by step. So it'll probably take about 8 videos, but yeah, if you got $5 you want to waste on something, you know, this is it. So first off, back at the old video, the center pin of the 3 terminal over here, that's power, and it also connects to one of the pins over here on the 2-pin connector. And well, we don't want to be putting a lot of voltage. This connects directly to the IC, which is over here, and we certainly don't want a lot of voltage there. So what I've put in is a resistor here and a Zener. The Zener is a 13-volt Zener, and at this point I'm just figuring it's about 20 mA it takes in. So this should be anywhere from 1,000 ohms to 1,500 ohms, depending upon how the final configuration is and what your voltage is. I got 2 solar panels, and their power point is like 20 volts. A lot of the new ones are higher in voltage and lower in current, so those who are stuck on PWM are going to be in a bad shape because they're going to get a lot of low power panels because PWM just works on current. So what I did was I cut the trace here and the trace here. You can see it darkened, and you can just use an X-Acto knife or something like that. I use power tools. This is an angle grinder, and this is a diamond blade, and it's really nice. It cuts through a lot of things very quickly, so you'd have to be careful with that. And you need a nice wide area that doesn't have any other traces near it. But I cut those out, and so that makes it very convenient. These 2 connections would normally connect together, and those go to the heater element. This is the power, and that normally would feed these capacitors directly, but we do it through a resistor because we want to limit the voltage onto this chip. The other thing I've done is I've shorted out this thing. I like to have a good ground, and if I'm trying to make voltage measurements or something like that, resistance measurements, this thing will turn on and off, so it's not really needed unless you're really goofy and you put things backwards all the time, but that's pretty hard to do. And this little arrangement in the Zener will protect the IC, and the FETs, they'll just conduct on their own. So you'll blow some fuses or something. If it's solar, they'll just get hot, so no big deal. So I've put this jumper over here. This FET I may use for something else. There's a way to use it with some of your control systems, but right now I have the thing hooked up, and if you look right here, we're getting a square wave out of it. It's 50 hertz, and it says it's a 51.5% duty cycle. And what that means is times 2, that 1.5%, that's the dead band, is actually doubled, so you get 3% dead band on that. And that dead band is controlled by this little resistor here. We'll talk about that later, but right now this video is just concerned with cutting this trace and cutting this trace. Now that'll give us a nice free input that's not connected to anything, and that can go to our voltage pot that we set. So it'll make it a very neat arrangement. Like I said, I'm just jumpering out this FET, so I don't have to worry about turning on and off. I know that, you know, I'll have a common ground, and so I can make resistance measurements from this pin when it's not powered. But 13 volt center, 15 volt, whatever, you got to stay under 20 volts. I wouldn't go higher than 15. And the calculations are pretty simple. Whatever your power is. So, like I said, I did 40 volts and have an unknown resistor here. And I'm figuring 20 milliamps going through that resistor. And I'm going to have 13 volts across this center. So 40 minus 13 is 27 volts. 27 volts divided by 0.02 amps. And that tells us we should have a resistor of 1350 ohms. And closest is 1.3K. You can go down to 1.2, even 1K. The resistor will get hot. So at just 20 milliamps, you're going to do a little over half watt. So you use a 1 watt resistor, or you could use 2 resistors in series to dissipate the power a little bit better. But that's the calculation. And if you go above, these FETs are IRF 3205s. But if you went and put something in with like an IRFB 4321, I think this is 150 volts. I think it's at least, I think it's 104 amps that it's rated at. You know, that'd be pretty good. And so you could have any voltage you want up to 150 volts. And in one of my other videos, I showed this little, it's a little switching power supply. It's supposed to take 110 to 380 volts input and convert it down to 12. And I find those work very well. So yeah, if you get up around the 60 volt range, you might as well go to one of those switching supplies, because you'll start developing a couple watts in the resistor, and no need for that. And the regulation is really good. So first thing you're going to do is cut there. And like I say, down here, there's 2 of them. And this one over on the side here. Make a cut across there, and you'll have a terminal you can work with. So that's the end of part 1.